Hi Kidlets, this is your notes for Wednesday, April 30th. I apologize, I have bronchitis. It is very tough for me to talk. Your test is still next week. I should be back unless I'm absolutely feeling terrible on Friday. We left off before we made our ocean model talking about features of the ocean floor. So we talked about seamounts and how they were underwater volcanoes. We looked at this in Google Earth, and remember that your Google Earth homework is due Friday. We talked about the ocean basin floor and the mid-ocean ridge system, which is that long ridge system that runs all the way from Greenland all the way down to Antarctica and back up the other side, where we have new crust that's created. Mid-Atlantic Ridge is the most studied ridge system. It's the largest mountain range on the planet, 43,000 miles. So the next thing we're going to be looking at is ocean currents. And ocean currents are driven by changes in density. And remember that density, in terms of ocean water, is caused by changes in temperature and changes in salinity. So here we have the equatorial system, here we have the poles, so obviously this is a simplified model. So we have warm water moving from the equator to the poles where it sinks and moves back again. And then in terms of our salinity, we have the formation of sea ice, which is excluding water, but then when it melts, it is releasing fresh water back into the area, and then when it's freezing, it is leaving an area that's very salty because sea ice does not include salt. So ocean water movements can be separated into two different types of circulation. We have surface circulation and also deep water circulation. So we can think about surface water circulation as being like flows of water. So this is driven by wind. So this is the movement of water flowing from one place to another, just like wind is blowing from one place to another. And this movement is horizontal. So again, we have these two types of ocean water movements. We have surface movements, which are moved by wind. And these are only in the upper layer of ocean. So if you remember in the different layers of ocean and different sections of ocean we talked about, we had the surface layer, the surface mix zone. So the surface mix zone is the only area that's affected by these surface currents. So this is the upper layer of ocean, and these are very large, like taking up an entire ocean basin, huge, slowly moving gyres. So a gyre is just a circular motion of something. So these are our main gyres, and you can see these are all reminiscent of the ocean basin they exist in because it would actually take up the entire ocean basin. And it is related to the atmospheric circulation because it is wind that drives them. So here are all of our major gyres, and you can see that we've got red and we've got blue. So if you remember back from the last unit of wind, remember that things move clockwise in the northern hemisphere. So like here is California. So there's, sorry, that X is way off. California's more like over here. But we can see that next to us, we've got a cold current coming from Alaska. So we've got a blue line across from us, and there's red over here. So in your Google Earth homework, you were supposed to click on buoy data, and remember that's due Friday. You're supposed to click on the buoy data and compare different temperatures. And it's always significantly colder here because we're getting Alaskan water, whereas on the East Coast, they're getting Gulf Stream water, which is in turn blowing that warm air over Western Europe. So we can see that we've got then counterclockwise flows happening in the southern hemisphere, and then at the equator, it's just moving horizontally. There's no Coriolis effect at the equator. So here is looking at the atmospheric circulation, which is parallel to the oceans. So if we have winds blowing one way, our oceans are going to move the same way. So the wind is what is carrying the world's surface ocean currents. And that's what's really moving warm air and warm water to colder places. So surface circulation is driven by the Coriolis effect. So like we just looked at, remember we're looking at to the right or clockwise in the northern hemisphere, and to the left or southern or counterclockwise in the southern hemisphere. So surface currents are important because they have such a large influence over climate. So our low latitudes, and remember at this point you should know what the low latitudes mean, into higher latitudes. So it's transferring heat from warmer to cooler areas. So it's really responsible for this transfer of warm air and warm water to cooler places on the planet. So if you remember also during the last unit, during climate, we talked about El Nino. So upwelling is where you have, if you have a basin of water and we have this top layer here, Upwelling is taking this cold, very nutrient-rich water from the bottom and bringing it up. So if you remember from the last unit, El Nino is when this does not happen. So this is usually along the west coast of continents. So if here is our continent, here's our landmass, the water would hit that continent and move up. So it would carry with it all of that nutrient-rich, very cold, very dense water. And there are organisms that rely on that. So deep ocean circulation is a response to density differences, whereas our surface circulation is driven by wind. So these are our major differences there. So surface circulation driven by wind, deep ocean circulation, and remember this is about 80% of the ocean, is deep water, is driven by density differences. So the things that create a dense mass of water, again, are very cold waters, so temperature, and salinity, very salty waters. So remember, if we were looking at the vertical water column, we would have our coldest, saltiest waters here. Then we have our mixed zone, which that is where our pycnocline and thermocline happen, and then we have our surface zone, which is where our surface currents happen. So this is called thermohaline. So again, think about what the word thermo and haline mean. And the simple model of this is a conveyor belt, like where you pick up your suitcases at the airport, that thing that transfers things horizontally. Because whereas surface water stays within the same ocean basin, deep ocean water travels the entire planet. It takes about 2.5 years for deep water to travel the entire planet. So water that's been off the coast of California will be back off the coast of California again in 2.5 years. And the significance, remember we talked about the North Atlantic Current when we watched the movie The Day After Tomorrow, because this is where it starts, this is where it ends. So here is a little map showing that. The red would be warmer water, which is along the top, and the blue would be our colder water. So right here, the North Atlantic, is that driving source. And if you remember from the movie The Day After Tomorrow, they talked about how the buoys were registering a temperature drop, meaning that these currents in this area, where those buoys were reversing. So like out here where you would normally have really warm water, well, kind of warmer water for it being polar, was suddenly dropping. So because all of this ice in that movie was melting, so releasing with it tons of very cold, very dense water, even colder than it usually was, and it was changing that current, which then changed the global distribution of water, which changed global climate. So I wanted to show you this video on YouTube of the global ocean conveyor belt. So here we can see all of this surface water that is moving up to Greenland. So we have Greenland that's up here. And then we can see it all going underneath. So it was a surface current, warm surface water that right there plunges beneath and becomes cold, deep ocean water. And I like this animation because you can actually see all of the seafloor topography. We can see all of these seamounts. You can see the Mid-Atlantic Ridge System, all of which you're supposed to be looking at in your Google Earth homework. So we can see the surface water moving north, and then we can see our cold, very dense, very saline water that is underneath. And this is the global path of it. So our deep ocean water does not just stay still. It's traveling all over the planet. So here we can see it traveling this way. So right there, I'm going to pause it for just a second. Pause. Never mind, I'm not going to pause it for a second. But right there was where you had El Nino. You start to see those currents going to the left. That's exactly what that's what La Nina is. El Nino is when that doesn't happen. So here we can see one of those gyres. So here we can see water completely moving around Antarctica. All right, that is it, guys. Please be good for your sub. You need to be outlining the chapter on ocean currents. Then you guys will be watching the video, but you have to actually finish that outline first. You'll have 15 minutes to do your annotations for that. And then the video is about an hour. So you have to get done with those annotations before you watch the video, and the video questions will be due in your packet. So I should be back on Friday, and remember that your Google Ocean homework is due on Friday as well.